trees, you'll start to see it move. 30 trees, 100 trees, it's starting to pick up on what's going on. And around 300 trees, we have a pretty good set of predictions. The other thing you'll notice is that you're clicking through. The residuals are basically falling to something around 0. And so what you can see from that is these tree-based algorithms are carving your data up into different nodes, into different chunks, and they're essentially building different predictors for each of these chunks. And the bigger residuals get a stronger weight. So briefly, the algorithm, you're gonna, for a classification problem, for example, you're gonna normalize your data. All of this is building regression trees, which is the central piece of this algorithm. And then we cleverly compute weights for the outputs and wash, rinse, repeat. And as Cliff is going to tell you, this is interesting not only because I think you should have a sense of what a regression tree does, because it's the core of this algorithm, but because that's where the time goes. Everything else is a tiny little bit of computation around building regression trees. And if we could quickly walk through what a regression tree actually is, imagine I have this bag and I have some residuals, and on the first row I have my x's. Now the thing you should notice is I can only split when the x variable changes. So I have three opportunities to split: 1 to 2, 2 to 3, and 3 to 4. So this is sort of a view of what a regression tree is actually doing. It's carving it up into different pieces, left to right. It's sweeping over my potential cuts, and it's attempting to minimize a squared error over the residuals. So 1's on the left, 1's and 2's, 3 and 4's on the right, 1, 2, and 3, 4 on the right. And what it's finding, at least in this case, is that the minimal error is carving out 1 on its own, and everything else to the right available for a future pass. Similarly, what a regression tree is really doing here is it's carving up a pair of variables into sort of rectangles with divisions orthogonal to the axes. So there's a direct correspondence between the tree on the left and the division of space on the right. And then within each one of these 1, 2, 3, and 4 units of space on the right, it's building individual models based on the likelihood that you chose when you ran the model. Now, as much as I do like GBM, there are some serious pain points. It's slow to fit, and it's slow to predict. This is basically unsurprising because you're doing this sort of greedy search over some combinatorial explosion of an optimization problem. Particularly if you're willing to let there be fifth order interactions, you have something like the power of the number of explanatory variables you have to the fifth power, which is quickly enormous. It has severe data size limitations. You're often going to have to do downsampling, and of course the fear when you're downsampling is that you're throwing away data that otherwise would improve your model. Many implementations are single-threaded, so it kind of sucks to buy a very nice 32-core computer and watch one core sit there and work and the other 31 sit and spin while you're waiting for your model output. Finally, the parameters are relatively difficult to understand. So things like interaction depths, like how many sets of variables do you consider, are relatively straightforward, but the rest of them, what's going to work well for you, is going to be very data dependent, and you're probably just going to have to go look and do some sort of brute force search and measure the performance of your model over this space. Of course, with some ability to trade off the amount of time versus the quality and improvement in the model results, but this is going to make a slow job even slower. And so as compared to ours GBM, which is one of the very popular models, H2O is willing to work with up to 65,000 factors. We have it running in-house on very large amounts of data, over 100 gigabytes, and we'd be happy for it to work on much more. And we're seeing 4x speeds are faster on a single node, and it does scale with the number of nodes in your system. And that's it. So I'm going to hand things over to Cliff, and he's going to talk about an implementation.
Thanks, Earl. But before you step off, do we have any questions for Earl? So he didn't mention it, but he's our in-house math expert here. And okay, there's a question already.
Did you say it was multi-threaded? H2O?
Yes.
H2O is, yes.
Cool.
Any reason you're using like the square distance instead of other distance measures?
So you're using the square distance measure in order to make decisions because what you have is a set of residuals. And the residuals don't really have a known distribution. They're simply, what you're doing is you're building a tree, predicting and creating residuals. And then those residuals, you're using the squared arrow to decide what to carve up into nodes. With individual nodes, you're using the likelihood to make a predictor within the node. But as to where to make the cuts in your explanatory feature space, that's a squared arrow.
Sort of a related question. It sounds like you're at no point are you worried about taking the gradient of the loss function. So is there, I mean,
You are actually taking the gradient of a loss function. That's what it's doing in the nodes in order to compute the predictor.
So why would you be able to do that handling the missing values?
Oh, because it's a tree-based algorithm. So you can treat, so say you have a factor, and NA is simply another level of your factor, right? If you have a continuous variable, you can do something pretty similar. It's another value that you're going to be able to handle. A GLM, in contrast, is doing an actual computation. So, sorry, I hope everyone could hear. A GLM is doing an actual computation. So if you have a missing value in your matrix, you either need to drop that row or you need to put a value in there. Yes?
Can you talk about the shrinkage?
Sure. So what the shrinkage is doing is it's reducing how much you change your it's reducing how quickly you change your current prediction, and the idea is this will help prevent you from overfitting. The trend is to set it relatively low and let this take a while. And I think what people's experiences have been is that while it's not fair to say that it will never overfit, it is fair to say that it's very slow to overfit.
What do you typically use?
0.01, 0.001, but you know, you're going to have to run a number of iterations. It's at least one over that. I mean, that's not a hard rule. You can quit anytime you like, but just sort of reasoning about it. And so I would really let that be data-driven. I would sweep over it, and I would say, what works best for my data?
Awesome. All right. Thanks, Earl. Okay, so I'm going to shift directions.
Probably worth calling out Trevor Hasty, who is also peer reviewed.
Okay, so what do you mean on the implementation side here?
Yes.
On
the math side.
Yeah, okay. So this algorithm came from Trevor Hasty. His book on elements of statistical learning. I think there's a whole section in the book on it, and in particular, I'll show you the page. I think Earl flopped that page up, which is what we've implemented. And so we'll get there. Okay, so the shift in direction I'm going to go here is I'm the systems implementer engineering guy and not the math guy. So I'm implementing the math that people say works well, and I figure out how to make it go fast. So what really is going on here is GBM is building a thing we call H2O, which is this pure Java open source stuff. Here's the GitHub link. You can go download and play with the source code. And what it really is, it's a platform for doing math. So in particular, parallel and distributed math. And we're using it to do a lot of in-memory analytics. So GBM, but generalized linear modeling, random forest, logistic regression, there's a number of things, k-means. And the platform is drivable from a number of different directions, including REST and JSON, which from the REST and JSON paradigm, you can get to R, which we'll demo here in a little while. RStudio, I'll drive some demos from that. From Excel, from Python, from a number of other languages. So it's a very general purpose way to get at this thing. And then the parallel and distributed part is basically as much memory and system and cores as you put together in a cluster. Okay, so what I'm going to talk about then is some notions of doing stuff with big data. So what is the notion, how do we talk about it? Then I get a distributed tree algorithms for which GBM is one of them, and random forest is another, and there are others floating around. And then we'll get into specifics on GBMs on H2O and how fast and how long and so forth and so on. So the first thing we'll talk about here is big data. And how do I talk about big data? So H2O internally builds a thing we call a VEC. So this is this Java code I wrote up here. And a VEC is like, it's like a Java array, except it has more than 2 billion elements maybe. It's as many elements as fit in a log or in your cluster. And there's fast random access to get things and to put things. And there's a notion of missing elements because a lot of the algorithms need that. And they can be variable size, have some other interesting features. And the vectors are, we collect them and we align them in memory in a way that fits the notions you have about like an R data frame, about looking at your data. So there's some pile of these vectors all striped through memory, and they're aligned on, they're aligned in the JVMs, but they're striped across the cluster. So any individual vector here might be bigger than what fits on one machine, but certainly the collection of all of it is. However, when we stripe it this way, we can get access to a row across at fast access for any one JVM for that one chunk of data. But the one JVM, while he can get out the other data, it's a network traffic overhead. So the goal here is to have each JVM work on data that's local to himself and describe what they're doing, the math they're doing in a way that's sort of natural and easy without thinking about the boundaries that are breaking the data up here. Because if I did that, I'll never get my algorithms written. So within these chunks of data, I have, or within these vectors, I break things up into chunks. That'll show up here in a little bit. A chunk is typically 1,000 to 1,000,000 elements. And it contains my raw data. Internal to a chunk, I do some sort of compression. The effect of the compression is typically my in-memory data is no bigger than the gzipped file on disk, and often smaller, sometimes 2 or 3x smaller. So I get a fair amount of compression here. And despite the compression, I can pull it out in a few clock cycles, generally faster than my memory can stream it in to the CPU. So the compression is essentially for free in that sense. It didn't cost me anything to do the compression. And I win because I get more data. I can squeeze more data into RAM. Okay, so within the chunks, a CPU is going to work on a chunk. He's going to work on all the data across all his columns within a chunk. And another CPU is going to work on another chunk, and another chunk, and so on and so forth. And so pretty much I light up all the CPUs as I march to the data and do something with it. So this notion of a chunk shows up because it's my unit of parallel execution, parallel access. And then I'm not moving the data anywhere, and typically the codes move to the data, everyone runs their piece in parallel, and then they roll up results together, and that's what we're going to get to here in a minute. But it's all about talking about what I'm doing within a chunk. This is the main core of the algorithm. And then there's a roll-up phase for the data between the CPUs and then across the clusters, rolling up to the top level where it's being driven. So to summarize, I've got a frame which is very similar to an R frame. It's a collection of vectors. The vectors can be billions of elements long. They're broken up into chunks, which are big enough that I can do some sort of efficient batch processing on a chunk. But a chunk might be 1,000 to 1,000,000 elements. And element's conceptually a Java double, although it's actually, how it's stored in memory is up to the compression scheme. If I have a column full of booleans, it will be stored in memory as a bit set. And I don't think about it as a bit set. It's just happens to contain only 2 values. And when I say, get me the value, I get whatever the 2 choices are. And then I can talk about a row of all the elements of a vec going across. And my guarantee is that this will be efficient. If I talk about the same row on one CPU, I can march sideways through the data at essentially no cost. Okay, so within that taxonomy here, I have sort of 3 ways to look at the system. And the top easy level way is to say, I don't think about distribution coding at all. And this is using REST and JSON to drive whole algorithms. So I can go to the console, or I can go to my R console and say, please load this data set from S3 or HDFS or local disk or wherever it is. And the fact that it's being loaded in parallel across the cluster is not something I care about or I see. It's just going to get loaded that way, striped across the cluster. It's all invisible. It happens. It's done. And then I can say, run GBM or run DLM or do whatever, and we'll demo this in a little bit. And I'll get an answer back. And in that sense, I'm just cycling the system like it's a black box for doing math. And it's very useful at that level.
Probably a good time to poll if how many people would actually
prefer not coding at all in the audience?
That's a good point. Okay, so how many people here code or are interested in coding math at some level versus using it? So the coders, people who do coding for a living or were thinking about doing code for math. So like a third of the audience maybe. It's interesting. How many people here do math for a living and are interested in a black box that magically runs math faster? Aha. So I got fewer, several. Yeah, there's some scattered around. Okay, that's very
You
interesting.
should make it a little sexier. They'll probably.
I might
Oh, yeah,
shift
data
talks
science.
here. I went for the data sciencey talk, and I have the systems engineering version. We can go into more detail if you want. Okay, so this talk, much of what comes next is going to be how to do data parallel coding in a way that's sort of reasonably easy to look at. And in particular, it's going to be heavy on the MapReduce, but not your grandfather's MapReduce. So when I say MapReduce, I'm talking about nothing to do with Hadoop, but with the conceptually clean notion of map and reduce. So map takes as a function from my data to some value, and reduce takes pairs of those things, whatever they are, and folds them together pair by pair and gives me one where I used to have two. So this particular map is conflating the types. It's a little harder to see what the choices are, but it's just going to do the obvious sum of squares. And the map is taking some value, doing some function on it, and returning me something that might be of a different type. But this type matches this type, and the reduction takes pairs of these and folds them into one. And then I say do all, and I'm handed a vector, and this will run parallel and distributed across my cluster with no further work. So this piece of code just gives me sums of squares. And in fact, it will run at memory bandwidth speeds here. I can't actually make it run any faster. It's going to be milliseconds per gigabyte kind of speeds. But I can get more complicated in my inner loop, so let's look at that. So I can have state in particular, and in this case, the map is taking multiple inputs, however many inputs I want, and producing a this pointer, and he's updating in place in memory. So I'm showing again something fairly simple. It's the linear regression pass one, but I have something pretty complicated in here that I'm accumulating state on, and it's really in the this pointer. And the reduce is taking to this and to that, and folding them together. So a map will run over a chunk for 1,000 or a million elements in parallel with all other CPUs running their maps over all their 1,000 to a million elements. And reduce will take pairs of those million elements and fold them together in a logarithmic tree rollup. Most of the reduces will happen within your node, but when you've done all the work on your node, they'll start going across the cluster, pair by pair over the network, until they roll the results back to where you started from. So here it is with the chunks more exposed. So here's my batching, where I can say for I equals 1 to the length of a chunk. So I passed in chunks here instead of raw values. And then I fetched my double x and y out by calling chunk at and chunk at. And this is where my decompression happened. So this is under the hood. It's doing a bit set, bit vector lookup if that's what your data is stored at. And it's shift scale add or whatever the compression scheme of the moment is. And then you do the same map you had before, and the reduction's unchanged. So this is pretty efficient, actually. And this is just doing stride one axis through memory, and so is that. x86 is really good at prefetching that. This will run at memory bandwidth speeds and saturate your CPUs and do the math all at one go. And because it's a batch thing, I can do work outside the loop if I have some interesting loop invariant stuff to pull out, and know that that extra work is not happening everywhere all the time for every row. It's happening once per chunk, which are already 1,000 to 1 or 1,000,000 to 1 reduced from the original work. So this is a pretty efficient way to write things if you can contemplate your code as a map and reduce. All right, so I have more systems-y side and the kind of stuff you can do. Let me back up a slide here and go back and we'll pull the audience one more time. So I've shown some real basic stuff here, but I can get into more detail doing group bys and uniques across clusters and all kinds of cool things you can do in this paradigm in a very straightforward way. Because we're looking at GBM tonight, I'm going to turn over and head for GBM. But I can come back and talk about more of the kinds of things you can do in this paradigm that we're going to run like really fast across your cluster. So here's the algorithm. I think you saw this page before. It's this Hasty, Tiptrani, and Friedman. It's an eye chart in some ways, but most of the math here is really cheap and easy, except this one. Fit a regression tree where you have millions or billions of rows. And what is the cost and time of building a regression tree? How do we make that go fast? So what I'm really going to talk about now is how I contemplate, think about a tree on data that's striped across a cluster. And what I really do is I take the nodes of a tree, the leaves of a tree, and assign every row to whichever node on the tree it happens to land in. If it was walked down the decision tree, it ended up on some node, some leaf of that tree. So I give it a number, and I assign a node to the number by making a giant set here, and for each row, I've set it to whatever node I get landed on. And this is some temporary vector I've made. So by the way, this makes me a vector that's of size equal to the original guy, so it's a parallel temp. Except because it's all full of zeros, it compresses really, really, really well. So it's essentially free. It costs me almost nothing at all to make a zero vector of a billion elements. And then I make a pass over all the rows. So when I visit a row, it's at some node. I don't know which one. So the nodes are not visited in order, but the rows are visited in order. And because the rows are visited in order, I'm very efficient at touching my data. And then I'm going to do some work per row. And in particular, what I do is I grab histograms. So let's go look at what that turns into. So I have some initial tree here. And I've started all rows at node 0. And I've got some value of my predictor and some values of my response variable. And I'm trying to figure out how to split this tree up so I can make a prediction on my y based on just x's, right? So I make a sweep over all the data, and I accumulate sums and sums of squares, and I get average and variance out. Okay, fine. Using that information, I'm looking for a split decision. And one of the things I didn't say here is I've done the histogram building is built on x's as they're broken out by different choices. And I go through the same decision that you saw with Earl, where I walk down the line saying, if x is less than 0, less than 1, less than 2, less than 3, here's my error and my variance as I walk through, right? Based on that, I come up with some decision, and I decide to encode it in the tree. The tree is just a POJO, a plain old Java object. So I didn't do anything special about the tree except to define a Java object that looks like a tree and looks like a Java tree object, whatever. And I give it a decision. Hey, if you're column X and if you're 1.5, go left, else go right. And then I make another pass over all the nodes. And when I make the pass, I pick each node and apply it to this decision, and it goes left or right. And I assign a new node ID to it. And then I bin it again, according to which piece it landed. So I end up with a histogram for every node in the tree, and whatever rows landed on that histogram pile in, and they get an average and a variance for that particular node. And then, looking again at this set of data, this is my small data. It's only 2 right now. It's 2 elements of the tree. Even though there might be a billion rows in each set, I end up with 2 things, and I look each one, split it or not. Looks pretty clear that node 2 doesn't need to be split anymore. It's got a good decision. Variance is very low. If I just predict 1.2, I'm like spot on. Whereas the other guy is pretty big variance. So maybe I decided to chop this guy off. But I'll keep going with the other guys, make another pass through all my data, and decide to split it again and get a different predictor value for the leaves on that. And so on, as I add layers to the tree. So what really happens is that I need a pass of my data for each layer in the tree, but every pass is fully data parallel. So as I add more data, if I add more nodes, I divide the work of the data by the nodes that I've added, and I keep dividing the work per layer to get my speed up, right? So sequentially, I'm going down, but each sequential pass is as fast as I have nodes to divide the data up amongst. Okay, yeah, so this is what I said. Each pass is a layer in the tree, but I'm building them one at a time here. This is a short eye chart form of the pass. I'll touch it real quick and then we'll move on here. So I have a map call over my data. And so I've just made a pass thing which comes from MapReduce task. He's got some node IDs. He's pulling out one of the chunks here is my data. So all my columns are my chunks array, so my node IDs is temps. And I'm rolling over all my rows, grabbing out the length of the rows there. I pull a node ID out for this row, and then I go ahead and make sure there's a histogram. Not all chunks will see all nodes in all trees. Some chunks will all land here or land there. So I'm lazily producing my histograms. But once I got a histogram, I go ahead and do whatever accumulate does, which in this example is going to compute, bin my predictor and then compute sums and sums of squares for each of the different pieces so I can make a decision later. And I just say do all on my data frame and my extra temp variables And this is running now across the cluster. And I'll show you examples which are very similar to this, straight out of the H2O code base here if people are interested. But this is pretty dang close to what the actual code looks like.
So this code is independent from the specific number of columns you have.
Yes.
Before, if I'm not missing something, you were naming the columns. That X was a column, Y was a column.
Right. So here I said my data frame, this had some number of columns, and I don't care how many. So 10, 100,000, whatever. Here, this array will have one chunk for every column, 10, 100,000, whatever, plus however many extras I have for temps. Turns out I have a few extra columns thrown out here that I'm not showing. Depends on how many classes I'm trying to classify at once. But the count of columns is independent. So this code here is independent of the count of columns.
Yeah, which I think is the first example where you get to this level of generality, right? Before, you were assuming, right, the members to argument, does that mean 2 columns?
So, okay, so all the algorithms we're showing tonight, except for like there's the demo ones that are really tiny, but all the algorithms we actually implemented are all completely independent of the count of columns. So you can have 1,000 columns, 10,000, 100,000 columns, and they'll just work. They'll burn more memory, they'll take more CPU if you add more columns, but that's because your data is getting wide and not necessarily tall or deep, but they'll do the same thing. Does that make sense to people?
Also, I just want to confirm, so you're still having to calculate one tree before you can calculate the tree's residuals? Like
Yeah,
you're just kind
right.
of like paralyzing the
Yeah, so this is,
individual tree, but...
right, so this is the difference between RF and GBM, is there's not really a way to parallelize the GBM trees independent from each other. Like one of the main goals of the design.
Residuals.
It's because you're doing the residuals with each tree. So here I'm showing an accumulated histogram. As part of this pass, I'm going to run through and say subtract my prediction from the actual value and get a residual. That's what's feeding into the decision here on how I split things. So I can show the code where I make exactly that call, but that residual has to be available from the prior tree before you can start the next one. So the random forest, really, one of its design goals is to run all the trees in parallel. So they are utterly independent, right? And that is its strength and its weakness. Okay, so for GBM, one of its strengths is the trees are dependent, and the next trees are picking up the bits that the prior tree couldn't clean out, right? So conceptually, the first few trees clean out the high-order function out of your signal, out of your data, and the remaining trees are picking up all the things that aren't high-order signal, the secondary effects, right? But that means they have to come in order. And that in order is some serialization process that I can't really break with some sort of parallel trickery here. So instead I went parallel across the data. So there is a limit to how fast I can build trees, and it's how fast I can turn an individual layer over. In practice, if your data is small or your count of machines is large, it can be pretty quick. And the same speed as R or better, actually it's actually very competitive with R on small data on one machine. But as you get more data, no one can get by a machine with less than 4, 8, or 16 CPUs these days. As soon as you get enough data to go over like what I would call a chunk, immediately I'm doubling and then doubling again, because I got CPUs to burn when computing that histogram. Okay, so we talked about this already, so maybe I'll roll through it pretty quick. Layer at a time in the tree. Use that one tree to decide how to build the next level. Reassign rows level by level as you go. There's actually only one pass there. And then end up building a histogram per node. And then all the histograms for one level are done in parallel, however many leaves are on the bottom of each of the trees.
Since you rewrote some of the random forest code after this, maybe you could probably once again explain from the histogram code how you have GBM and random forest go differently.
Okay, so that one probably, so the question is, can I explain the difference between GBM and random forest? Maybe it makes more sense to pull the actual code up to go there, because then I can show you, oh, here's a residual calculation. It's very obviously where I'm saying prediction minus, actual, I got a residual, that's feeding into the next pass. Whereas random forest, it's done a different way, where you're just predicting each guy based on, but you're selecting your columns at random. So that's a different criteria there. Along the way of talking about building distributed tree algorithms, I built a bunch of utilities for helping me build trees. One of the main ones here is I'm going to score and build in one pass where I take a row looking at the prior decision made from the last pass and splitting it left or right, according to which way it goes. Once it's assigned to a new leaf, I build some sort of histogram on that leaf. Both RF and GBM algorithms use the same notion, although what they use for computing in the histogram vary, and what decisions they're allowed to split on vary. I have utilities to help you score a tree or predict on it. The trees themselves, you can easily get thousands of trees in these models, and they can get quite large. In random forest, if you go deep, each tree might have 100,000 leaves, and in GBM, it's common to have 1,000 trees or more in a model. So you can imagine the models get big, so I compress them. And there's some really tight compression you can do on a tree, and then I can walk and score and print and do things with that tree, but the actual size of the tree, once I'm done compressing it, is pretty small, it's reasonable. And there's a bunch of utilities to mess with it. Okay, so the summary here is that GBM, it builds one tree, one level at a time, but each entire level is parallel distributed. And that also means that I'm doing the tree entirely breadth first, because it's free to go breadth first as opposed to depth first. And you can offset more data by adding more CPUs. Pretty much, I can get fairly fine-grained and still make good forward progress. So it's kind of free to add CPUs to speed it up or add data to match their CPU size, right? Otherwise, it's classic GBM, straight out of the book. We followed it line by line. We're building things just the way the book did. All the tuning knobs are there for trees and depth and shrinkage and all kinds of stuff. And I think we're getting time to go to demo mode. Okay, so let me summarize a little bit on the writing of math here. Most simple Java in those inner loops just works. I have written all kinds of stuff. They've gotten quite complicated. It's never been an issue to think about how to write the math in the inner loop. Once you figured out that the data is striped around your cluster, your for loops look like what they look like. You just wrote them however you write them, and they work. Reads are pretty much same speed as plain Java rate loads because the decompression is hidden by memory bandwidth latency issues. Writes are pretty close, a little bit slower because I do compress behind your back. And that means my temps, when I write data into temp columns for whatever reason, it gets compressed behind your back too. But typically I'm memory bandwidth limited anyhow, so the compression's all hidden. I do follow the strict Java memory model rules across the entire cluster. So if you have conflicting writes, you'll follow what the Java memory model does, which is fairly loosey-goosey, so it might not be what you want, but at least you know what the guarantee is. And I do transactional updates if you ask for it, for people who need to do, and we use this transactional updates all the time to do all the control logic hidden behind the system. So there's a lot of stuff in there that makes it look easy that's relying on transactional updates. Okay, so we're writing big data analytics. We've written state-of-the-art algorithms. This is like the newest of the new and the best algorithms we can find. And we have them running distributed. We're solidly working on 100 gig. Actually, I think we're testing now, nightly tests are like 180 or 200 gigs on a regular basis, right? And we're heading upscale as we go. Okay, so let me switch to demo mode. And unfortunately,
I'll close the mic.
why don't you hold the mic while I set up, because I had to shut off my Wi-Fi here.
As Cliff begins to put his thing up, startups and all projects are team sports. None of this was built by one person. I would like to have a roll of hands from 0xdata team and a growing set of open source contributors for our project. Please raise your hands, 0xdata team. And Mikhail, I see Tomas there. Tomas for the GLM. New Tongshin. Tongshin is the latest new member. Well, of course, you know, Irene is our math geek. Angie and Spencer are back there. Cliff and I started this company after finding no tools after staring at an R screen for more than 12 hours or 16 hours myself and trying to build simulations that took weeks at length. I mean, all science has been now the lowest common denominator is data science. Data collection is cheap. Data science is the only science left. So we want to build great tools and make them available in Apache V2 so you can embed it, use it, plug it into R. I mean, the future looks like it'll just be a R wrapper, basically another package that implements cool packages in R, so you guys can access it from R and Python and Excel. We are not yet another big data startup trying to do something cool while it's popular. We are going to be around. We're going to build this math library till we find the right math for our time. I think one of the things missing in this whole discussion is GBM is the cutting edge algorithm, and that's why we're starting there. But what if the math that's needed to solve our big data problems is missing? And that's kind of where we want to encourage the audience to be part of this. GBM didn't come out of the blue. We asked the audience when we were building random forest, what would they like to see in addition trees. That was 4 months ago, so the last 3 months was building GBM. And the next 3 months could be the algorithm you guys want. So please be part of the overall conversation. And it's a product's not complete without the community behind it. So with that, I'll give it back to Cliff here.
Well, you want to talk while I use 2 hands to drive this thing? So here I'm going to install from scratch on RStudio. So I have a completely clean RStudio, and I'm going to do an install here. The tar file that comes with the tar file came here comes with H2O. You download it from the web and you get it. You're going to install a package. I'll come on this side over here. Ta-da. And we're going to do...
How's the font? Should we increase the font?
People can see this in the back? Sort of, kind of. I think 1 or 2 font size increases wouldn't hurt anybody. Does that look all right? Okay, so, yeah, that's when we go on here. So there's a couple steps to install. Find your package, load the dependent packages. So the main package pulls in some other stuff we need. Part of the things we're doing here is like R curl, and this is where we're going to use the REST and JSON to talk to and from a cluster. So what you saw in the background was that we have a cluster running up in our lab, and so I was getting a VPN connection to it, so we can show some big data being driven by R.
Are you connecting to localhost or to the back?
To the back end. So it should be, so here's the IP address from our back end cluster as forwarded to VPN. Should be 161, yeah.
It's 60024.
Different
The port, okay.
Yeah, 60024. It's a number.
Yeah.
What's the number?
Yep.
Yep. Go. And the magic of VPN.
In big data, CEOs have to demo.
Bam. Okay, it's up and running. And this says we're connected to this cluster. So this is the small data demo. Aha. Uh-oh.
I know what's going on.
Okay. Oh, right.
Uppercase O, right?
Yeah. All right, now try this. No, you didn't do the...
Let's do this.
Yeah, didn't do the initial launch. Yeah.
Are
So-
you testing Streetcliff?
Yes, I am.
What's going on?
One of the init steps needs the local thing. All right, where's Angie?
No, I think you
We're
probably
gonna do this locally from my laptop here in a second.
No, I think you probably need the server local.
Yeah.
Yeah.
Just hit tab. There you go.
That's it.
Yeah.
It's the
Yeah.
data. There's the data. Got info.
Isn't this the demo? Oh no. No, where's the data? All right, you got to. Yeah, you can't do it that way.
Local host, right?
You want to do this from local here?
So I guess we can import data from HDFS. That's probably the first step, right?
Yeah. Now you need the local H2O.
Okay.
And then I guess it's path. HDFS colon something. So we have an HDFS at our office that we test against. We can load data locally. This one is, the cluster is running, I think it's Airlines Hall. The cluster is running at the office as well as the Hadoop server, but they don't have to be co-located, although they can be. H2O does all its own internal clustering. And so we don't require Hadoop. We work fine on S3, we work fine on local data sets. You can run a one-node H2O cluster on your laptop for nothing more than java-jar, h2o.jar, and it'll come up and be ready to go. And in that sense, it's a very fast way to run GBM. Okay, so this is coming from the cluster now.
So this is,
And here is the cluster. It's a 4-node cluster of 200 gigabyte machines. So it's actually a pretty big cluster. And I think there's going to be,
so it's
we're pulling in the data set. Okay, so R has asked for this data set to load from RStudio, and we're pulling in. This is a couple gigabytes worth of data, like 12 or something.
It's all 120 million rows of
Okay.
airline data.
And this will take a minute or two, and if we look, there's some system load, and some CPUs are busy, and some memory, free memory sizes will go up and down according to GC cycles, and the data is piling in, and getting spread around the cluster.
Where is the perf bar?
It's on the VNC tab. Yeah. So somebody's stuck doing I/O. It's however fast HDFS will hand us data.
Done.
I don't know, maybe you're done. I'm wrong. Oh, you're done. Go find what RStudio says. RStudio says, okay, so you loaded 12 gigs. You want to do like a head of that?
Okay.
And so this went into the H2O cluster and said, give me the first 6, 7 rows of the airline data set. So 120 million rows.
Should run a summary.
Run a summary and let's take a look. So summary is going to compute more interesting stats over the whole data set. And we can, oh, there it is. So 120 million rows. You got first quartile, median, mean, max quartile.
I want to show the audience how it actually looks here.
Yeah. So here we have a web GUI that does JSON in and out, or pretty prints the web, pretty prints the JSON as HTML. So you can drive it this way, which is really convenient for point-click shooting on things. And then if you hit the JSON button upper right corner, you'll get this all piled out as piles of JSON. So it's convenient to drive it this way and look at the JSON if you're making a script that's using REST and JSON to drive things. But this was 120 million rows, and we've broken out like histograms of which
This is
column is
American
this?
Airlines.
Oh, okay. This is the carrier. So 12% of all flights were done by American Airlines in the last 20 years, and here's Delta at like 13%, and whoever else. That's like Northwest U.S. Airways, maybe in Northwest.
Yeah. So essentially, that's what you.
So this particular data set is the accumulation of flights for the last 20 years, including their on-time behavior. And one of the fun things you can do with this is go do a prediction on the on-time behavior of flights and see if you can figure out who's fast and who's slow and wide. Okay, there's the last zillion rows.
Okay. So now time for GBM, I suppose.
Yeah.
I'm gonna call names.
You want is departure delayed is on the screen there. Do you want to drive it from here?
So X is all of them.
Yeah, just do all for now because it's going to be a lot easier. And it won't be a realistic model.
It won't be realistic.
Okay. So the easier thing to do here, so if you're doing, so the particular thing about the airline data set is that they also included with the departure delayed or not, a bunch of information about why it was delayed. And so if you're building a predictive model and you have information telling you why it was delayed, then you were delayed. So if you're predicting delay, you just have to look over the next column and see that, oh, I have a delayed code, so therefore I'm delayed, right? So it makes a very unrealistic model. So the goal here is we're going to try to look at predicting a model where we're predicting on-time behavior based on things that are not available to you 24 hours in advance, right? So don't get to cheat and look for the delay code, but try and figure out why you were delayed or not. So Shree's stepping through the different delay codes here: diverted, canceled codes. You can have taxi. That's probably in there, maybe. Probably okay. Sure. I don't know. I don't think that one makes a difference. It's the wrong keyboard. It's a Mac guy on a Windows box, as opposed to the Windows guy on the Mac box.
The revenge of Cliff, right?
I think some more CRS times. I think that's it. And scroll down.
Okay.
Yeah, you're good.
Explain.
Okay, so number of trees you want to build, the max depth of the trees, minimum observations on a leaf, the amount of binning points you're going to split at, the learn rate, which is pretty high here compared to what people do, but we're trying to get a demo on some length of time. So it flips to this mode, and then it starts lighting up tree cores. So you want to flip to the VNC session here for a second here? Okay, so yeah. So here I am running data parallel across 12 gigs of data, 120 million rows of data. And the little like doinks, that's stopping to roll up the data and declare a tree split and go to the next one. And every 5 or 6 of these, maybe it's like 8 or 9 of these, you get another tree level done. There's some number of these passes here to make a tree. I don't have the right count of them. But it's going to be building trees as we go here. And we've got some trees built. And because the shrinkage is there as 0.1, you can imagine, that means that the predictive quality of a tree is reduced by 90%. So each tree only moves the bar just a little bit away from the median to try and get a better prediction. And the reason for that shrinkage is to avoid overfitting, but it also means you have a lot of trees to get a reasonable fit. So in the beginning, we pile on trees, the fit's pretty bad, and we're slowly creeping in on it. And of course, the refresh is like wiping the screen down, and you can't shrink the font. But you can see it's still pounding away here and lighting up all the cores. I guess these are 32-way machines. Yeah, it's 4 times 32, so 128 cores, like going to town.
The entire operation on the hardware front was less than 30 grand, so it's not a very expensive machinery, but it's state of art. Today's probably 1 minus today's machineries. So these are not expensive. These are Linux Intel boxes. And typically we find our customers use one of those boxes in hope of getting their GBM go faster, but it usually lights up 1 core. And Tom's a perf bar artist, so we decided to use perf bar for the demo.
I think that's the big pieces of the demo. Why don't I take questions from people for a while here? People too excited about the perf bar going up and down.
It is hypnotic.
Any final questions?
How big was the data set again?
12 gigs on disk. In RAM, maybe you can open another tab, show the data in RAM.
So essentially airline data set is a popular data set for playing in the space where basically you're trying to use all 20 years takeoff and landing flights. And that's about 120 million journeys. Our journeys, and basically this data set has compressed 5 gigs, but really 12 gigs on disk. People usually sample that data set so they can run GBM, they can run GLM. On this platform, it takes 5 seconds to finish a GLM on the entire data set, logistic regression, on all 700. I think it's roughly 700 categorical columns when it expands. So in terms of factors, so it's a pretty high-speed system that Cliff and the gang have put together. So we would love. I mean, this is available for download on our main website. It's open source, and we want people to use it. It's almost like G8 as of today, and so you should try and use the product. GBM will show up in the browser. I think if you had a local host, the demo would have worked on RStudio as well.
Yeah, I don't have a local JVM running, but I test and play with RStudio, just running my H2O on my laptop.
So questions?
Any other questions?
Yeah.
I saw mentioned that you also parallelized random forest calculation.
Yeah, random forest is designed to be parallelized, and we parallelized it in the obvious way. So you just run the trees in parallel. You build the trees in parallel. They're all independent.
Have you done comparison on the same data set with your parallelization of random forest versus GBM in runtime and in accuracy?
I have not, because GBM's too new.
It's what I asked Earl to do at 4 p.m. today, and he said next meetup.
My experiences have shown increased accuracy, and it's slower.
For GBM.
For GBM.
GBM,
So
more
you're
accuracy and
have to decide
slower.
what it's worth to you.
Yeah, with RF like tops out at some count of trees, and adding more trees doesn't seem to help it.
RF has some very neat tricks, but the thing that any boosting algorithm is going to get you is it waits where you're wrong. Yeah. And RF is fundamentally going to be unable to do that. But that costs you the iterative nature.
Yeah.
But on big data, is it possible that random forests could get you really good results?
Absolutely.
So yeah, I think so the last Thursday's talk where Trevor, by the way, major kudos to the Stanford math team, which works very closely with us, Dr. Boyd, Trevor Hasty, and Rob Dipshirani. Trevor basically corrected and made us build the exact textbook algorithm that Cliff has for you guys. And I mean, finally got on stage, and till it was actually the page number 387 on ELS third edition book, he was not satisfied. And so it was done and approved. So in that sense of it, major kudos to the team that's not here as well, but it's our advisors in Stanford who have done a terrific job. But with that, I think we're running short of time.
Let's thank our speakers.
Yep.
And
thank you.
So these guys are going to be around for a little while to answer any remaining questions. The doors are going to stay open until 9, so feel free to drink some more beer and socialize. Quick note, I got an email just a minute ago that the BART is going on strike tomorrow, just so you guys know. Strike tomorrow. So, all right, thanks guys.
By tomorrow, it means 4 hours.
Yeah. You don't have to go home, you can stay here.
Well, but they aren't helping you get home either.
Thank you, everybody.
Hey, nice to meet you, Sean. Yeah, so,
Say if we can get a picture with you
love
guys.
it. It sounds like you're getting pretty much similar.
It'll make me happy.